Hello everyone, thanks for coming here today. My name is Vira Shyta and I'm the first year master student at the Department of Theoretical and Mathematical Physics at the Kiev Academic University. So today I'm going to tell you about why we consider topological Chern-Simons theory is important, what physical systems they help to describe, and later I will proceed to talking a little bit about duality properties of these systems and quantum phase transitions in those. So first of all, we can start from this paper by Redlich from 1984. In this paper, author considered the connection between the spontaneous breaking of space-time symmetry, the coordinate reflection invariance, and the gauge model invariance. So he studied the 2+1 dimensional gauge series coupled to fermions. And what he found is that the action for systems with odd number of massless fermions is both gauge transformation variant and coordinate reflection variant, while the effective gauge field action obtained by integrating out the fermions is either gauge transformation variant or the coordinate reflection variant. So it means that there is a symmetry breaking going on there. And he showed that the effective action of such system contains the following Chern-Simons term, which you can see here on the slide. This term is also called the topological term, and it's known to violate symmetries in systems, and that's the general form of this term. So it's non-abelian. If we want to refer to the abelian Chern-Simons term, that's the first part of this term without the trace. So that's the Chern-Simons term, and that's the term which we'll see in Lagrangians all over the world. Where we can find those. For example, we all know that in two-dimensional electron gas, in low temperature and high values of magnetic fields, we can get the quantum Hall effect. The resistivity goes in plateaus, and we know that the effective theory of fractional quantum Hall liquids. So when this filling factor nu is a fraction, the Lagrangian is described with the following formula. What we can see here is that the Chern-Simons term, where small a's are the vector potentials of the emerging gauge field, and the couple A is the vector potential of an external magnetic field. So here we see that those Chern-Simons term here, abelian Chern-Simons term, about which we'll talk later, is coupled to the K matrix. That's an integer valued matrix, which defines the topological order properties in the system and defines the correlation and connection between different quantum Hall states, fractional quantum Hall layers. So like that's the important part, because later in my work you see that the same term arises in a completely different system. So also the topological Chern-Simons appears in describing the topological superconductors. First of all, what is a topological superconductor? Well, that's a gapped superconducting bulk with gapless and topologically robust quasi-particles propagating on the bulk. And the following paper by Key, Witten, and Jen, published in 2013, describes the effective action for the 3+1 dimensional topological superconductor. They obtained it from this model. So basically, they made this model of sandwich with 4+1 dimensional topological insulator with Weyl fermions with opposite helicity propagating on the boundaries and yellow ones. And they showed the surface effective theory of this 4+1 dimensional model is the 3+1 dimensional superconductor. And it contains the topological term. So what we did in our work is we decided to do something similar, and also like thinking about the dimensional reduction, we looked at 2+1 dimensional case. So basically we considered the following Lagrangian. The first term here is a usual Higgs term, which appears when I want to describe superconductors. The second term, this one. That's the known for you already abelian Chern-Simons term. That the one which appears in those odd space-time dimensions theories with topological terms. And this term is considered here for gauge invariant. So what we were looking at the first part of my work is we were trying to find the exact solutions or just the solutions for field equations, which you can obtain from this Lagrangian. And we were looking for vortex solutions. What I mean by this is that we assume that the curl of gradient of this superconducting phase is not zero, but it's quantized and it looks like this. So it's not zero, where m and m naught are some integer values, so quantization numbers. So we were looking for solutions with one vortex or with two vortices, and we in two plus one dimensional theory, and we obtained the following result. So for one vortex, you can see the electrical potential amplitude of the electric field. So it's two-dimensional, so electric field is like in plane, and the magnetic field is a pseudo-scalar, so that there is like it's pseudo-scalar here, not a vector. So basically here, red is like positive values, blue is negative values, and something whitish is around zero. So the idea is that we were able to exactly solve these field equations and express electric potential, electric field and magnetic field in terms of the modified Bessel functions k not k1. And the similar things we obtained for two vortices, which look like that. They also were expressed in terms of that modified Bessel function. But here, when we were considering these solutions, we were thinking about like static vortices, but vortices can also have dynamic. They can move. They can be time dependent, and the electrodynamics of the vortices can be very important to characterize the physics of the system. And one good example of this with dynamical vortices is a very quite known Brzezinski-Clausius transition, for which the authors got the Nobel Prize in 2016. So here we also have two-dimensional physics system, but at low temperatures, your point vortices, which you can see here, are tight in pairs, so they're coupled, they're bound together, and we can think about these point vortices, which move in this plane as of point charges. And basically here, when they're tight, you have like the electric phase, and here at higher temperatures, when they decouple, when they're like single vortices only, their dynamics looks like some Coulomb gas for what we notice. So this theory is for low temperature. This theory is for high temperature. And what we see here is that that's like duality between, there is a connection between high temperature fluctuations and low temperature fluctuations. And this, and there is a phase transition between them. And it was only possible like to explain because of this vortex dynamics. So that's why it's so important to consider. And it also allows us to talk a bit more about what duality is. So basically, duality maps theories with weak coupling to theories with strong coupling. Theories which look the same for weak and strong couplings are called self-dual, and like the famous example of this is the two-dimensional Ising model, from which you can get the relation for critical temperature. And some theories look very different when you do the duality transformation. Like here on the slide, you can see that if you consider the 2 plus 1 dimensional XY scalar XY model on the lattice, here and do the duality transformation, you get gauge Higgs theory with all those gauge fields and vortices which are produced from the periodicity of this phase. And so remember, duality maps strong coupling to weak coupling theories. And here you see how the coupling constant is inverted in the dual transformation. And there is the connection between these two theories. So it's interesting how physics in like for weak couplings is actually related to the strong coupling theories. And this tool of applying the dual transformation is very important and useful if you want to talk about phase transitions. So before when we consider the BKT, Berzin-Stalis transition, we were talking about phase transition induced by thermal fluctuations. But here now we consider quantum phase transition. What it means is now the phase transition goes at 0 temperature, and it is induced with a variation of some external parameter. It could be pressure or external magnetic field, or change in the concentration of electrons or holes. Today, like from the previous talk, which was done by Lisa, she talked about phase transition and like the dependence of her crystal phase structure from the whole concentration, if I remember correctly. So that's exactly what it is. Yeah. So usually we have the recipe how to classify those phase transitions, or first order like rapid transition, or second order phase transition when you have like smoothly vary the parameters and there is a continuous transition and you have the quantum critical point here. And usually we can classify those with the theory suggested by Landau and Ginsburg. So it associates the critical singularities with fluctuations of some order parameter. For example, in magnetic systems, it can be magnetization. And its behavior encapsulates the difference between the two phases in ordered or disordered states. And usually and it's associated with the spontaneous symmetry breaking in the theory, but sometimes there are phase transitions without symmetry breaking, and there are some systems which we cannot, for which the predictions of Landau-Ginsburg theory are incorrect. The example of such theory is a theory with competing order parameters, for example, which we can find in two-dimensional, 2+1-dimensional antiferromagnetic systems, which you can see here. So basically, one phase is a Neil-Brown stain, so that's antiferromagnet, and it has a long-range magnetic order. And here you have a paramagnetic phase. So here the fluctuations of spins, they do not allow to develop the long-range order parameter. Yeah, so this paramagnetic state is called valence band solid because the nearby spins, they form a singlet like there, so they bounce and we have the valence band solid. So a paradigmatic lattice model for such a scenario is provided by the so-called JP model, whose spin one Hamiltonian also includes not only just nearest neighbor interaction as an Eisen model, but four-spin interaction, as you can see here. So why this slide is called Deconfined quantum criticality? That's because those critical points, so basically Landau-Ginsburg theory suggests that this phase transition should be first order phase transition. So there is no critical point. And it's not a continuous transition. But in reality, we know that that's a second order phase transition. And we have this quantum critical point. Here, for example, that's like the ratio between the coupling points. So this quantum critical point is called deconfined for the reasons related to a mechanism very similar to one occurring in studies of the deconfinement transition in high energy physics. So this type of quantum critical points is called deconfined. And in this case, order parameters on both sides of the transition, like the antiferromagnetic one and the VBS state ones, they fall apart into a more like elementary particles, which we call spinons, and we speak of spinons deconfinement. So basically, those spinons are confined in both phases, and the deconfinement only occurs in this particular quantum point. And I'll talk more on the next slide about what I mean by spinons and how they occur. So it is one of the well-studied theories in the context of spinon deconfinement is a non-compact CP1 model. It is called non-compact because here the gauge field is not a periodic field, and that implies a suppression of instantions. So the idea is that you can get this easy plane and compact CP1 by conducting by doing the CP1 representation of a nonlinear sigma model with easy plane anisotropy, which you can see on the slide. So the idea behind the nonlinear sigma model is that it's the effective theory to describe antiferromagnetic models near the critical point. Usual nonlinear sigma model looks just like this, where n is a magnetization vector, and there is like a constraint on it that the module of this magnetization is 1. But here we can also reduce the symmetry of the system by adding this term. So that's called the easy plane anisotropy. And we can do the CP1 representation. Basically, we say that we introduced new fields, these are spinons about which I was talking about. And we can express the order parameter, the magnetization, as follows. We get a new constraint, and that's called the Hopf mapping. So basically, you map the two-dimensional sphere into a three-dimensional sphere, because remember that Z, those spinons, that's some scalar field, complex scalar field. And like after doing this, you get the nonlinear, non-compact CP1 model, which is written in form of those spinons, and A is the emergent gauge field, which can be expressed through those spinons. And if you were looking only at this, at the CP1 representation of this nonlinear sigma model without the anisotropy, what we would get is the confinement critical point, and the spinons would be deconfined in one particular point, and you get the second order phase transition. But here, this model is self-dual, and people were predicting that maybe this system with easy plane anisotropy is going to have a second order phase transition too. But if you do the numerics, you get that's the first order phase transition. So what we thought is maybe if we define this system a little bit different, maybe it will have a second order phase transition. And just as we did it, like the general grand picture is that after this second part of our research, we will notice that there is a connection between this particular model with Chern-Simons term, the topological superconductor with two component order parameters, and also the whole bilayer quantum state. So stay with me. So what we considered is this Lagrangian, which has the non-compact CP1 model, CP1 representation, and the Chern-Simons, a median Chern-Simons term, which we have seen before. So at first we had this initial model. We just did the polarization. We went to the polar coordinates, and we looked at the regime of strong anisotropy. So K much bigger than G, and we get the following effective action, which only depends on the phase fields, those thetas coupled to the gauge field. And here already you can see that at first we looked at this model, which is connected to the antiferromagnets in 2+1 dimensions with time reversal symmetry breaking. That's what the Chern-Simons term does here. We also know that the similar Lagrangian is connected to the chiral spin liquids. And now, when we just look at the strong anisotropy regime, we see that this effective action is quite similar to what we saw at the two-dimensional topological superconductor. You again have this Chern-Simons term, and you again have this kind of Higgs term, but now with two different order parameter components, two different superconducting phases. That's already very interesting. But if we do the Duality transformation, that becomes a real thing. So like if we do the Duality transformation, where we introduced the vortex loops, we see that this initial system is due to the 1-1-1 quantum Hall state, which underline a bilayer quantum Hall system. And here we get this term I mentioned when I was talking about fractional quantum Hall effect. you get this K matrix, which in our particular case is only has all elements are equal to 1. And we see that our antiferromagnetic system with time reversal symmetry breaking looks very simple, very similar to the two-dimensional two+1-dimensional topological superconductor with 2 ordered parameters, and it's due to the system of quantum of bilayer quantum Hall states. Here, these terms they refer to the vortex gauge field. Here, V it's again like. As I mentioned, the curl of gradient is non-zero. That's the connection. That's how this term appears here. And W is the curl of this V. That's non-zero of the curl of the gradient. That's like vortex loops, and they reappear in the dual action. And we kind of can say that our vortices are coupled to the electric field here. So what is so interesting about this duality, and why should we be excited about? So the cool part here is that in 2000s there were many papers which noticed that there is a Josephson effect, which we can see in quantum Hall bilayers, and there are no superconductors, and that's kind of surprising. But now we know that it's not that surprising, because the quantum Hall bilayer systems are actually dual to the topological superconductors. So that's very interesting thing that we can already see here. But let's return, let's continue with this new dual system. The determinant of K matrix vanishes, it's 0, because everything is 1, 1, 1. And therefore we can introduce a diagonal basis, like a new electric field, electromagnetic fields, B plus, B minus, which are defined here, and these new superposed vortices. And if we rewrite this new obtained dual effective action and do the following scaling, we can see that there are 2 different types of modes. One of them is gapless and refers to the Goldstone modes of this system, and it refers to B minus. And the B plus mode, the gapped mode, is topologically massive. So we have 2 different types of modes. And if we do the rescaling here and introduce the new coupling constant E, we can say that the dual action has gauge fields coupled to an ensemble of vortex loops. And after this rescaling, they can be reinterpreted as word lines of charged particles which interact with electromagnetic fields B plus, B minus. And this is this is the essence of the particle vortex duality about which I was talking before with the example of BKT transition. So the path integral for a many particle system interaction with gauge fields is more conveniently studied in terms of quantum fields associated to the sum over the word line ensembles of the particles. So we can rewrite we can obtain the dual field Lagrangian from the previous action. And if we look at the limit cases of kappa going to 0, we'll get just the model which is dual to the usual easy plane non-complex CP1. But if we look at K going to infinity, we get a theory dual to a O2 nonlinear sigma model. And this O2 nonlinear sigma model has the second order phase transition. So that's already all very interesting. And if we look at the renormalization group invariance of this Lagrangian, we see that Chern-Simons term is called topological, right? Because it does not depend on metrics. And if you think about renormalization like a rescaling, in terms of energy, it's kind of intuitively, you can intuitively understand that this Chern-Simons coupling term after renormalization does not change, does not renormalize. So, and we can write this in equivalent form like this. After we do the renormalization group equations, we can find the flow of G and the coupling G. And it has a fixed point, and it has a quantum critical point. And as we have this connection between couplings G and kappa, we see that kappa also has the fixed point and it also has a quantum critical point. So we can argue that this new system, at which we were looking at, non-compact CP1 with Chern-Simons, actually has a second order phase position. So the main takeaway of this topic is that Chern-Simons NCCP1 with easy plane anisotropy is exactly dual to the system of 1-1-1 quantum pole states underlying a bilayer quantum pole system, and it leads to interesting connections in papers which were already published like 20 years ago. And Chern-Simons NCCP1 with easy plane anisotropy exhibits a deconfined critical point. So I thank you, the UKRATOP project and the IPW, all people who made this possible. This has been a very great experience for me, and I feel like I've learned things which I never thought I will. And I'm surprised of how much there is still to learn. And so thank you all, and thank you for your attention.
Thank you, Vera. And we already have the first questions online. So please go ahead.
Thank you, Vira. It's very impressive. I mean, first the level of your talk, and also that it is very close to what we are trying to actually merge here. I mean, topological materials and superconductors and Josephson junctions. But unfortunately, I could not follow your formulas, especially so fast. So that's naive questions about vortices. Do your vortices have something similar with abrikosa vortices?
Yeah, when we talk about topological superconductors, of course, it has, because when we think about topological superconductor, we can write actually like London equations for the second order for the second type superconductor, but there will be additional topological term in it, and it will change the behavior of a topological superconductor in comparison to the usual superconductor. But the vortices are similar.
So they have one quantum flux quantum carry, right?
Yeah.
And about opposite vortices. So you show these pairs; they are opposite vortices, and what prevents the annihilation?
So in the system at which we were looking at this model, there is actually we couldn't see the actual interaction between these vortices. They are opposite because their sign is defined by this quantum number and this integer number, but it actually could be the same sign, and they will not be opposite. They will look at the same direction. The problem here is that we were as we were looking at the static case, there is no interaction between these vortices. It more looks like a superposition of vortices now. So we didn't consider that. So there is no annihilation or attraction between them in our system, although probably there is actually if you look at the dynamical vortices.
Mm-hmm. And also one more then question: what about the idea what about the result that on topological superconductor the edge of vortices should be charged? So you have then opposite charges on these vortices, or?
Yep.
Okay. Okay, thanks.
Special thing, right?
Yeah.
The vortices are charged, and then the opposite flux has opposite charge as well. Don't you guys talk about this electrical charges? You have electric fields.
Oh. Okay.
No, remember there's electric. You have a panel with electric field.
Yeah.
There's a major difference.
Yeah. They are electrically charged now too. But there is not only the magnetic field, but also the electric field. But we didn't actually consider the interaction between these vortices. Hasn't come up yet.
Oksana has a question.
Yes. First of all, thank you for the talk. It was very impressive and interesting. And I have a few naive questions. First, that could you please say more what you mean by ordered and disordered phase? So is it, for example, paramagnet and ferromagnet, or this is?
That's exactly antiferromagnet and ferromagnet, for example. It's just like here the idea is that Landau theory not always predicts correctly the order of quantum phase transition. And one of the systems in which it predicts the first order phase transition, but there is actually the second order phase transition, is the transition between the antiferromagnetic ordered state and the paramagnetic disordered state.
Thank you. And also, could you please show slide with QJ model? QJ, yes. So my question is, what means this -1,4 in the second term? Because maybe it's not so clear what we need to add this -1,4 to.
The JQ model is just a paradigmatic model to explain these things, but like in our model, we did not like look into it. So that's just the example that like to account for this interaction and to look at this deconfined criticality, people have this JQ model, for example.
Thank you.
But it's not like the point of what we were doing.
Okay, do we have questions from the audience on site?
I want to hear your expert opinion. I'm very impressed by what you did. So, in your expert opinion, do you think that there is a point to prove it's there, or do you think?
We think it's there, but we are almost there. Like we had a few different ideas about how to show it, and the problem is that there is something arises in U. For example, we were doing at first, like usually the Duality transformation is done on lattice for such cases, but like Chern-Simons has a very strange behavior. So we had to go to the continue things, and like it changed during like at first we had the idea that we can show that a dual system is going to be maybe simpler than the initial system, and it will be easier to show the second order phase transition, but like it wasn't. There is also peculiarities, but now we are almost there. We think like we'll look closer into this renormalization group, and maybe there is like even simpler idea to show this second order quantum critical point without like going into too deep of renormalization group.
Okay, so then the duality is kind of an extra feature that you stay with the original model and do that.
Yeah, but it may help us argue like more like additional more intuitive ideas.
Absolutely.
Okay, Vitaly also has a question.
Vira, thank you for your beautiful talk. I have a question about parameter order. What is parameter order in your model with Chern-Simons term model where you investigate on the duality transformation?
Well, yeah. Here we moved from that. We had this ordered parameter magnetization in our easy plane and isotropy nonlinear sigma model, but we went to the CP1 representation, and from here on we introduced the auxiliary B fields, and basically when we do the renormalization group, we look at the behavior of the couplings in the dual system. So we look at the renormalized this renormalized constant, like this coupling of the Chern-Simons term, and we look at the renormalization of U and V couplings, and just trying to find the fixed point for them. If it answers your question.
So thanks a lot. I think we need to move to the next speaker. Thank you.